The morning of August 23rd, 1944. A Panther Ausführung, a serial number 215984, sat motionless on the proving grounds at Aberdeen, Maryland. The tank had travelled less than 300 kilometres since rolling off the production line at Daimler-Benz in Stuttgart 6 months earlier. German crews had abandoned it during the retreat from Falaise in Normandy, claiming transmission failure. American recovery teams found it intact, started the Maybach engine without difficulty, and shipped it across the Atlantic for evaluation. Captain Thomas Harrington, of the United States Army Ordnance Corps, stood beside the disabled Panther, watching as Sergeant Mike Kowalski and his team prepared to remove the final drive assembly. Harrington had been testing armoured vehicles at Aberdeen since 1942. He understood tank engineering, understood stress analysis, understood what separated reliable machinery from fragile equipment. The Panther represented everything German propaganda claimed about technical superiority: thick, sloped armour, a powerful 75mm gun, sophisticated suspension, advanced optics. On paper, it was the most formidable tank in the world, but the Panther sat immobile because something in its final drive had broken. Not from enemy fire, not from combat damage, from normal operation. The final drive was the critical connection between the engine's power and the tank's movement, a series of gears that reduced the engine's high-speed rotation to the lower speed and higher torque needed to turn the massive drive sprockets that moved 45 tons of steel and armour across the battlefield. Every tank had a final drive: British Churchills, American Shermans, Soviet 34s. The engineering was straightforward, proven. The Germans had been building tanks since 1935. They understood the principles. Harrington had reviewed the technical intelligence reports from Europe. German tank crews were abandoning Panthers at alarming rates, citing mechanical failures rather than combat damage. Normandy battlefields showed Panthers sitting intact beside roads, tracks undamaged, hulls unpenetrated, but immobilized by broken components their crews could not repair in field conditions. Something was fundamentally wrong with the design. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The removal process revealed the first problem. Sergeant Kowalski reported that accessing the final drive required disassembling the entire front of the tank. The driver's compartment had to be stripped. The transmission had to be lifted out. Components that should have been modular and replaceable required complete disassembly of surrounding systems. Harrington had supervised final drive replacements on Sherman tanks. The procedure took experienced mechanics approximately 1 hour, using basic tools. The Panther's design required a full day of work with specialized equipment. The final drive assembly emerged from the Panther's hull after 6 hours of careful disassembly. 2 mechanics carried it to the inspection bay, a cylindrical housing approximately 18 inches in diameter and 14 inches long, weighing close to 100 pounds. The exterior showed no obvious damage, no cracks in the housing, no signs of impact. The problem was internal. Harrington directed his team to mount the assembly in a precision vise designed for detailed mechanical inspection. They removed the housing cover, exposing the gear train inside. What they found contradicted everything they expected from German engineering. The Panther used a double-spur gear reduction system, 2 stages of straight-cut gears that reduced engine speed through direct tooth-to-tooth contact. This was the simplest possible design for a final drive. Mechanically unsophisticated. The kind of gearing found in agricultural equipment and industrial machinery where simplicity mattered more than efficiency or durability. Harrington had expected to find an epicyclic planetary gear system, similar to what the Tiger tank used. Planetary gears distributed load across multiple gear teeth simultaneously, reducing stress on individual components. They were more complex to manufacture, requiring specialized gear-cutting machinery for the internal ring gears. But they were dramatically more durable under high-torque conditions. Every American tank designer understood this principle. The Sherman used planetary final drives, so did the M26 Pershing being developed for heavy combat. Planetary gears were proven technology for vehicles weighing over 30 tons. The Panther weighed 45 tons in combat configuration. yet it used spur gears designed for vehicles half that weight. Sergeant Kowalski pointed to the intermediate gear, the second stage of the reduction system. Multiple gear teeth had broken completely, sheared off under load. The fracture surfaces showed characteristics of fatigue failure rather than sudden overload. The metal had been stressed repeatedly until microscopic cracks propagated through the gear teeth, weakening them progressively until they failed catastrophically. Harrington examined the broken teeth under magnification. The gear material showed poor metallurgical quality. The surface hardening that should have protected the teeth from wear was inconsistent, with soft spots where the hardening process had failed to penetrate adequately. The core material lacked the toughness needed to resist crack propagation. This was not a problem of design tolerances or manufacturing precision. This was fundamental material deficiency combined with inadequate design for the application. The team documented their findings methodically: photographs of the broken gears, measurements of the gear dimensions, metallurgical samples sent to the materials laboratory for detailed analysis. Harrington drafted a preliminary report for the Ordnance Department. The conclusions were stark and unambiguous. The Panther's final drive was fundamentally inadequate for the tank's weight and power. The technical intelligence section provided context that made the failure comprehensible. German tank production had been rushed to meet Adolf Hitler's deadline for the Kursk offensive in July 1943. The Panther's original design by MAN had specified planetary final drives. But Germany faced critical shortages of the specialized gear-cutting machinery needed to produce internal ring gears in large quantities. The production planners, pressured by Karl Otto Sauer, the chief director of armament and war production, had mandated simplifications to accelerate manufacturing. The planetary final drives were replaced with double spur gears. These could be manufactured using existing equipment from Panzer III and Panzer IV production lines. No new machinery, no delays, no complications. The simplification allowed Panther production to begin months earlier than would have been possible with the original design. But the spur gears were designed for a 30-ton tank. The production Panther weighed 45 tons. The gears were overstressed by 50% from the moment the first vehicle rolled off the assembly line. Harrington's team calculated the gear loading conditions. The Maybach HL230 engine produced approximately 700 horsepower at maximum output, though it was governed to about 600 horsepower under operational conditions. This power had to be transmitted through a 7-speed gearbox, then through the final drive to the drive sprockets. The reduction ratio in the final drive was approximately 4.7 to 1, multiplying the torque delivered to the sprockets while reducing rotational speed. At maximum power in low gear, climbing steep slopes or maneuvering through difficult terrain, the torque loads on the final drive gears exceeded their design capacity by substantial margins. The gear teeth were being loaded beyond their fatigue strength every time a Panther operated under combat conditions. The testing program at Aberdeen included durability trials that simulated combat operations. A captured Panther Ausführung A arrived in September 1944, shipped from France after being abandoned by its crew near Metz. This tank appeared mechanically sound. The engine ran smoothly. The transmission shifted properly through all gears. Recovery crews reported no obvious damage. Harrington's team conducted standard mobility trials. Cross-country running over terrain that simulated European conditions. Road speed tests. Hill climbing. Sharp turns requiring high steering loads. The same evaluations every American tank had to pass before acceptance for service. The Panther performed adequately during initial trials. The ride quality was harsh, consistent with British evaluation, reports from Chobham. The steering required significant effort from the driver. But the tank moved acceptably across the test courses. Failure occurred during the 50-kilometre endurance run. The test protocol required sustained operation at tactical speeds across mixed terrain, rolling hills, soft soil, gravel roads, the kind of varied conditions tanks experienced during actual operations. The Panther completed approximately 40 kilometres before the driver reported strange noises from the drivetrain, a grinding sound during turns, vibration through the hull, classic symptoms of gear distress. Harrington ordered the test halted immediately. The team towed the Panther back to the maintenance facility and began disassembly. The final drive inspection revealed the same pattern as the first tank: broken gear teeth, fatigue cracks in the intermediate gear, bearing damage from the vibration caused by failing gears. This Panther had travelled less than 100 kilometres total since leaving the factory. Most of that distance had been road marches in France before the crew abandoned it. The Aberdeen testing added only 40 kilometres of actual operational running. Yet the final drive had failed completely. The pattern repeated with additional captured Panthers throughout late 1944 and early 1945. Every vehicle tested at Aberdeen showed final drive problems within minimal operating distances. Some lasted 200 kilometres. Others failed after 50. The average lifespan before requiring final drive replacement was approximately 150 kilometres. American tankers reported similar observations from Europe. Sherman crews who captured Panthers and attempted to operate them against German forces found the vehicles required constant maintenance. The final drives needed frequent inspection and adjustment. Even with careful handling, they failed regularly under combat stress. The most telling evidence came from German sources. Intelligence officers examined captured German maintenance records from panzer units in Normandy. The documents recorded final drive failures as the primary cause of tank losses during the retreat from Falaise. One panzer regiment reported replacing 13 final drives in a single month on 30 operational Panthers. More left-side drives failed than right, suggesting that the torque loads during left turns exceeded the capacity of the gears. A German technical report from June 1944, captured at a Wehrmacht vehicle repair facility, stated explicitly that Panther final drives had a limited service life. The report noted that the system was not very tolerant of jerky steering movements in heavy terrain. German crews were instructed to avoid aggressive maneuvering that would stress the final drives. Sharp turns at high speed were prohibited. Steering during hill climbs required careful technique to prevent gear overload. This was not the language of confident engineering. This was documentation of known design inadequacy, acknowledged by German engineers, but never adequately resolved during the war. Harrington compiled his findings into a comprehensive evaluation report issued in December 1944. The conclusions were damning. The Panther's final drive represented a fundamental design flaw that could not be corrected through incremental improvements. The double-spur gear system was inherently inadequate for the vehicle's weight and power requirements. The only solution would have been to redesign the entire final drive using planetary gears, requiring retooling of production facilities and months of delays. The German High Command had made a calculated decision: accept mechanical unreliability in exchange for earlier production and higher numbers, build tanks that looked formidable on paper but broke down regularly in service. The alternative would have been fewer Panthers delivered later, but with dramatically better reliability. The decision reflected broader patterns in German tank development during the war. Emphasis on specifications that appeared impressive in technical documentation: thick armour, powerful guns, advanced features, but insufficient attention to maintainability, reliability, and operational sustainability. The Germans designed tanks for proving grounds and propaganda films. The Americans and British designed tanks for sustained combat operations with field maintenance capabilities. The evidence was undeniable. Every captured Panther tested at Aberdeen failed mechanically before completing standard acceptance trials. Not one achieved the reliability standards required of American tanks. The final drives failed consistently at distances that would be completely unacceptable for operational vehicles. British testing had revealed similar problems. French evaluation after the war would document the same pattern. The Panther's final drive had an average fatigue life of 150 kilometres. This was not enemy propaganda. This was verified engineering data from multiple independent sources testing multiple different vehicles. The profound irony was complete. German propaganda portrayed the Panther as technically superior to Allied armour. Newsreels showed Panthers crushing opposition. Training films emphasized the tank's advanced engineering. Yet American engineers examining captured Panthers at Aberdeen found mechanically unsophisticated components stressed beyond their design limits, failing at distances that would qualify as infant mortality in American production standards. The Panther was not a triumph of German engineering. It was a case study in the consequences of prioritizing production speed over design adequacy, of accepting known flaws rather than delaying deployment, of building weapon systems that looked impressive but could not sustain operational use. Harrington understood that the findings at Aberdeen represented more than technical analysis. They represented tactical intelligence that American tank crews needed desperately. If Panthers had weak final drives, combat tactics could exploit that weakness, force them to maneuver aggressively, make them turn sharply, keep them moving in difficult terrain. A disabled Panther was as combat ineffective as a destroyed Panther, and Panthers disabled themselves regularly through mechanical failure without requiring enemy fire. The quiet work at Aberdeen Proving Ground, methodical disassembly of captured equipment, careful documentation of failure modes, was providing American forces with knowledge their enemies never intended to reveal. The vaunted Panther had a fatal flaw, visible only to those who looked beneath the armor and examined what German propaganda never showed, the actual engineering. The winter of 1944 brought additional captured Panthers to Aberdeen Proving Ground. Each vehicle told the same story. German tank recovery units in Europe were reporting final drive failures at rates that exceeded all other mechanical problems combined. A Wehrmacht report from January 1945, captured by American intelligence near the Ardennes, documented the crisis in stark administrative language. From the Panther, 370 final drive breakdowns had been reported in recent months. General Wilhelm Thommerle explained in the captured document that in such circumstances, an orderly utilization of tanks was simply impossible. The troops lose their confidence and, in some situations, abandon the whole vehicle just because of this problem. Captain Harrington read the translated German reports with professional interest. The Wehrmacht was acknowledging publicly, at least within their own command structure, what American testing had confirmed independently. The Panther's final drive was a catastrophic weakness that undermined the entire vehicle's combat effectiveness. The metallurgical analysis from Aberdeen's materials laboratory provided deeper understanding of why the failures occurred so predictably. The gear steel showed inconsistent heat treatment. Surface hardness varied significantly across individual gear teeth, with some areas achieving proper case hardening, while adjacent areas remained relatively soft. The core material lacked adequate toughness, making the gears brittle and prone to crack propagation under cyclic loading. Dr. Robert Chen, the civilian metallurgist assigned to the Panther evaluation program, explained the implications to Harrington during a review session in February 1945. The Germans were experiencing critical shortages of alloying elements needed for high-quality steel production. Nickel, chromium, molybdenum. These elements provided the toughness and hardenability that distinguished premium gear steel from ordinary structural steel. By late 1943, German steel mills were substituting available materials and experimenting with modified heat treatment processes to compensate for missing alloys. The results were predictable to any metallurgist. Inconsistent material properties. Gears that looked acceptable on visual inspection but lacked the internal structure to resist fatigue failure. Some gears lasted longer than others, simply due to random variation in local material quality. But all were fundamentally inadequate for the application. Chen showed Harrington microscopic photographs of fracture surfaces from broken Panther gears. The images revealed classic fatigue crack patterns. Cracks initiating at stress concentration points on the gear teeth. Progressive crack growth through thousands of load cycles. Final catastrophic fracture when the remaining material could no longer support the applied loads. The fracture surfaces showed beach marks, the distinctive rippled pattern that documented crack growth over time. These gears had not failed suddenly from a single overload event. They had died slowly from cumulative damage, weakening progressively until complete failure became inevitable. Every kilometre driven, every turn executed, every slope climbed, added incremental damage that brought the final drive closer to catastrophic breakdown. The engineering team at Aberdeen conducted comparative analysis to understand how the Panther's design compared to Allied approaches. Sergeant Michael Torres, a transmission specialist who had worked in civilian truck manufacturing before the war, led the comparative study. He examined final drives from Sherman tanks, Churchill tanks, and the developmental M26 Pershing. Every Allied tank used planetary gear systems in their final drives. The Sherman's final drive used a planetary reduction with multiple planet gears distributing load across the internal ring gear. When the Sherman's drive sprocket transmitted torque, the loading was shared among 3 or 4 planet gears simultaneously. If one gear tooth was stressed to 100% of capacity, the adjacent teeth were carrying proportional loads. The stress distribution was inherently balanced. The Panther's spur gear system concentrated all load on a single pair of meshing teeth at any instant. When the intermediate gear engaged the output gear, only one tooth on each gear carried the full transmission load. The stress concentration was extreme. The contact pressure between gear teeth exceeded the material's endurance limit under heavy torque conditions. Torres prepared detailed calculations showing the stress differential. In the Sherman's planetary final drive, individual gear teeth experienced peak stresses of approximately 120,000 pounds per square inch during maximum torque transmission. The gear steel's endurance limit was approximately 150,000 pounds per square inch, providing a safety margin of 25%. The Panther's spur gears experienced peak contact stresses approaching 200,000 pounds per square inch under similar loading conditions. The gear steel's endurance limit, compromised by material deficiencies, was approximately 130,000 pounds per square inch. The gears were operating 50% above their fatigue strength every time the Panther maneuvered under load. Harrington incorporated these calculations into his comprehensive evaluation report. The technical analysis demonstrated that the Panther's final drive failure was not a random manufacturing defect or isolated quality control problem. It was systematic design inadequacy, compounded by material deficiencies. The gears were too small, too simple in configuration, and made from steel that was too weak for the application. The report included recommendations for American tank development. The analysis validated the decision to use planetary final drives in all American medium and heavy tanks. The additional manufacturing complexity was justified by the dramatic improvement in durability and reliability. A Sherman's final drive typically lasted 3,000 to 5,000 kilometers before requiring overhaul. The Panther's final drive failed after 150 kilometers on average. The reliability differential was 20 to 30 times better for the American design. Testing continued through the spring of 1945 as additional captured Panthers arrived from Europe. One vehicle, a Panther Ausführung G captured near Cologne in March, provided particularly valuable data. This tank had been used by an American armored unit for 2 weeks after capture, operating alongside Shermans during the Rhine crossing operations. The American crew reported their experience in detailed after-action interviews. Lieutenant James Morrison, the tank commander, described the Panther as impressive in specific characteristics, but fundamentally unreliable. The gun was excellent, accurate, and powerful. The optics were superb, better than American sights. The frontal armor provided confidence that German anti-tank guns could not penetrate it at typical combat ranges. But the Panther required constant mechanical attention. The crew performed maintenance every evening after operations. Oil leaks around the engine required regular top-ups. The transmission made concerning noises during gear shifts. The steering required frequent adjustment to maintain proper response. Most critically, the final drives developed vibration and grinding noises after only 200 kilometers of American operation. Morrison's crew turned the Panther over to Aberdeen after the final drives deteriorated to the point where continued operation risked complete breakdown. The tank arrived with approximately 300 total kilometers on the odometer since leaving the factory. The final drives were already failing. Disassembly confirmed the pattern. Both final drives showed advanced gear tooth damage. The left side was worse than the right, consistent with German reports that left turns created higher stresses. Multiple teeth on. The intermediate gears had cracks visible under magnification. Complete failure would have occurred within another 50 to 100 kilometers of operation. The accumulating evidence painted a complete picture of the Panther's mechanical reality. The tank could perform adequately for short periods, under controlled conditions. A well-maintained Panther with fresh final drives could execute tactical missions covering 50 to 100 kilometers, but sustained operations over multiple days, the normal expectation for combat tanks, were impossible without frequent mechanical intervention. German units adapted their tactics to accommodate this limitation. Panzer regiments kept extensive stocks of replacement final drives. Maintenance platoons became expert at rapid final drive replacement, developing techniques to complete the work in hours rather than days. Some units transported Panthers by rail for even short movements of 25 kilometers to preserve the final drives for actual combat. These were not the characteristics of a reliable weapon system. These were symptoms of a fundamentally flawed design that required extraordinary support infrastructure to maintain minimal operational capability. The comparison with American logistics was stark. Sherman tanks required normal maintenance, oil changes every specified interval, track adjustment as needed, periodic inspections of major components. But American armored divisions did not maintain large inventories of replacement final drives because Sherman final drives did not fail regularly under normal operation. The reliability was built into the design, not compensated for through extensive logistics support. The tactical implications became clear to American intelligence officers, analyzing the data from Aberdeen. German panzer units were operating under severe mechanical constraints that limited their tactical flexibility. Panthers could not execute sustained operations without mechanical breakdown. Long road marches consumed final drive life that would then be unavailable for actual combat maneuvering. German commanders had to balance the distance traveled to reach battle against the remaining mechanical capability available for fighting. American units faced no such constraints. Sherman crews could march 200 kilometers to reach a combat zone, fight an engagement that included another 50 kilometers of tactical movement, then continue operations the following day without mechanical crisis. The operational tempo that American armor could sustain was impossible for Panther-equipped units. This advantage was invisible on a proving ground, where both tanks sat side by side for comparison. The Panther's specifications looked impressive, but specifications measured under controlled conditions did not capture the sustained reliability that determined actual combat effectiveness. American tank design philosophy emphasized the unglamorous engineering that kept vehicles running day after day. Accessible components, modular replacement, conservative stress margins, proven technology. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The German approach had prioritized impressive specifications, maximum speed on paper, thick armor at optimal angles, powerful guns with high muzzle velocity. But the engineering underneath the impressive exterior was compromised by production shortcuts and material limitations that made sustained reliability impossible. Captain Harrington's final comprehensive report on Panther mechanical characteristics, completed in May 1945, provided American tank crews with detailed tactical guidance. The report was classified and distributed to armored unit commanders, preparing for what was expected to be continued fighting in Europe. The German surrender in May made the tactical recommendations moot for European operations, but the engineering analysis remained valuable for future tank development. The report's conclusion was unambiguous. The Panther represented a case study in flawed development priorities, technical sophistication in some areas, crude simplification in others. Impressive performance in specific parameters, catastrophic weakness in fundamental reliability. The tank had been rushed into production before critical design problems were resolved, then fielded in combat before adequate testing verified durability. The consequences were documented in abandoned Panthers across European battlefields. American recovery teams examining German equipment after the surrender found Panthers sitting intact beside roads throughout Germany. Many showed no combat damage, no penetrations, no fire damage. just broken final drives that German crews could not repair in field conditions and abandoned rather than waiting for recovery units that no longer existed. One particularly telling discovery occurred near Munich in late April 1945. American forces found a German tank depot with 12 Panthers awaiting final drive replacement. The facility had adequate stocks of replacement final drives. The mechanical expertise was available. But fuel shortages and the collapse of German logistics meant the work could not be completed. The tanks sat immobile, technically repairable, but operationally useless because the infrastructure supporting them had disintegrated. The French army provided additional validation of Aberdeen's findings in the post-war period. France operated approximately 50 captured Panthers from 1944 through 1947, using them in military units stationed in occupied Germany. The French had access to German spare parts stocks and could employ German mechanics with Panther maintenance experience. They operated under peacetime conditions, with time for preventive maintenance and careful handling. The French War Ministry issued a comprehensive evaluation report in 1947. The document, titled simply Le Panther, analyzed every aspect of the tank's design and performance. The report's assessment of the final drive was devastating. The truly weak spot of the Panther is its final drive, which is of too weak a design and has an average fatigue life of only 150 kilometers. The French report noted that this limitation made the Panther unsuitable for strategic operations. A tank that required final drive replacement every 150 kilometers could not be considered operationally reliable. The maintenance burden exceeded acceptable standards. The French eventually phased out their captured Panthers in favor of American-supplied Shermans and French-designed vehicles, despite the Panther's superior firepower and armor protection on paper. The Aberdeen evaluation program had revealed a profound truth about military equipment design. Technical specifications told only part of the story. A weapon system's true value emerged from sustained operation under realistic conditions. The unglamorous engineering that ensured reliable performance day after day mattered more than impressive capabilities that could not be sustained in actual use. American engineers who examined the Panther came away with respect for some aspects of German engineering. The gun was excellent, the optics were superb, the armor scheme was sophisticated. But these strengths were undermined by fundamental weaknesses in the drivetrain that made the entire vehicle unreliable. The lesson resonated through American tank development for decades after the war. The emphasis on reliability, maintainability, and operational sustainability that characterized Sherman design continued in post-war vehicles. The M46, M47, M48, and eventually the M60 all reflected design philosophy that valued proven technology and conservative stress margins over maximum performance specifications. The Panther's final drive became a classic example in military engineering courses, a case study in the consequences of production pressure overriding engineering judgment. The original MAN design had specified planetary gears specifically because the designers understood that spur gears would be inadequate. Production managers overruled the engineers, mandating the simpler system to accelerate manufacturing. The decision saved months in production timing, but it created a weapon system that consumed vast maintenance resources, limited tactical flexibility, and regularly abandoned itself through mechanical failure. The short-term gain in production speed resulted in long-term operational liability. Captain Thomas Harrington reflected on the Panther evaluation as he prepared his final reports in the summer of 1945. The testing program at Aberdeen had involved hundreds of hours examining German equipment, disassembling captured tanks, analyzing failed components, documenting design decisions and their consequences. The work was technical and unglamorous, but it had provided American forces with critical intelligence about their opponent's capabilities and limitations. The Panther had arrived at Aberdeen wrapped in the mystique of German technical superiority, propaganda portraying it as invincible, intelligence reports suggesting it was the most formidable tank in the world. American tankers feared it based on its reputation and impressive specifications. But systematic evaluation revealed the mechanical reality beneath the propaganda. A tank that looked formidable but could not sustain operational use. Engineering that appeared sophisticated but incorporated fundamental design flaws. Specifications that impressed on paper but could not be achieved reliably in practice. The testing had revealed truth that German propaganda never acknowledged and German engineering never adequately resolved. The Panther was mechanically unreliable. Its final drives failed predictably under operational stress. The problem was known to German engineers, documented in German reports, but never fixed during the war. American crews facing Panthers in combat could exploit this knowledge, force engagement in terrain requiring maneuvering, extend operations over multiple days. The Panthers would disable themselves through mechanical failure at rates exceeding combat losses. The quiet work at Aberdeen Proving Ground had transformed intimidating enemy equipment into understood mechanical systems with exploitable weaknesses. The Panther was no longer a mysterious superweapon. It was a 45-ton vehicle with a 150-kilometer final drive fatigue life. That knowledge was power. The end of the war in Europe brought unprecedented access to German military documentation. American technical intelligence teams swept through captured Wehrmacht facilities, collecting maintenance logs, engineering reports, and operational assessments that German units had compiled during years of combat. The documents provided internal German perspective on problems that Allied testing had identified independently. A report from Panzer Regiment II, dated March 19, 1944, documented the battalion's experience with Panther reliability on the Eastern Front. The unit reported that final drive units represented a very large percentage of mechanical breakdowns. From April 1, 1944, a total of 13 out of 30 final drives were exchanged, more on the left side than the right. The report stated explicitly that the system was not very tolerant of jerky steering movements in heavy terrain. The language was carefully bureaucratic, but the implications were clear. German tank crews were experiencing exactly the failures that American testing predicted. The final drives broke under operational stress. The left side drives failed more frequently because left turns created higher torque loads. The problem was systematic and well documented within German military channels. Another captured document, a technical bulletin from the Inspector General of Panzer Troops, dated June 19, 1944, provided even more explicit acknowledgement. The report noted that Panther engines had achieved acceptable service life of 700 to 1,000 kilometers after improvements to cooling and lubrication systems. But final drives remained problematic, failing at distances far shorter than engine overhaul intervals. The document recommended that crews avoid excessive stress on the drivetrain. Specifically, running the engine excessively, especially going down steep mountain roads and during fighting in heavy terrain. Abrupt steering movements, though unavoidable in battle, should be minimized when possible. Excessive stress on the drive shaft, connecting transmission to final drives, contributed to premature failure. These were not recommendations for optimal performance. These were instructions for minimizing known mechanical weaknesses. German crews were being taught to operate their tanks carefully, to avoid breaking components that should have been robust enough to handle combat conditions without special consideration. The contrast with American tank operations was absolute. Sherman crews received no special instructions about avoiding abrupt steering or limiting engine operation. American tanks were designed to withstand the full range of combat stresses without requiring gentle handling. Drivers could maneuver aggressively, climb steep grades at full power, execute sharp turns at speed, all without risk of catastrophic mechanical failure. Captain Harrington's team at Aberdeen compiled comparative statistics that illustrated the reliability differential. Based on data from European operations and captured German records, they estimated that Panther final drives averaged approximately 150 kilometers before failure under combat conditions. Some well-maintained vehicles with experienced crews achieved longer service life by avoiding aggressive maneuvering, but the average remained around 150 kilometers. Sherman final drives, by comparison, typically achieved 3,000 to 5,000 kilometers before requiring overhaul. The reliability advantage was 20 to 30 times better for the American design. This translated directly into operational capability. An American armored division could sustain combat operations for weeks without mechanical crisis. A German panzer division equipped with Panthers required constant maintenance intervention just to keep vehicles operational. The accumulated intelligence revealed that German commanders understood these limitations and adapted tactics accordingly. A captured operations order from 5th Panzer Army, dated December 1944, during the Ardennes offensive, included specific instructions about conserving Panther mechanical capability. Panthers were to be transported by rail whenever possible for movements exceeding 25 kilometers. Combat operations were to be planned, assuming that Panthers would require final drive inspection after every 50 to 75 kilometers of tactical movement. These constraints shaped German tactical planning in ways that Allied commanders rarely recognized during combat. Panthers could not sustain the operational tempo that American armor routinely achieved. German attacks had to account for mechanical breakdown rates that would be unacceptable in American units. The mechanical unreliability was not just an engineering problem, it was a tactical limitation that reduced combat effectiveness. The human cost of the final drive problems emerged from interviews with captured German tank crews. Sergeant First Class Robert Hayes, an intelligence specialist at Aberdeen, conducted extensive debriefings of German prisoners with Panther experience. The interviews revealed consistent patterns. Crews trusted the Panther's firepower and frontal armor protection. They felt confident engaging enemy tanks that could not penetrate them frontally. But they had no confidence in mechanical reliability. Multiple German tankers described the psychological burden of knowing their tank might break down at any moment, leaving them immobilized in combat zones where recovery was uncertain. One former Panther commander, Oberfeldwebel Klaus Richter, from Panzer Regiment 24, described operations in Normandy during June and July of 1944. His platoon of 5 Panthers had experienced 11 final drive failures during 6 weeks of combat operations. Some tanks had final drives replaced multiple times. The constant mechanical problems degraded combat effectiveness more than enemy action. Crews became cautious about maneuvering, avoiding terrain and tactical situations that might stress the final drives. This caution created tactical vulnerability. Panthers that should have been aggressive, using their superior firepower to dominate engagements, instead operated conservatively to preserve mechanical capability. The fear of breakdown made crews less effective even when their tanks were temporarily functional. Richter's account included a telling detail. His company abandoned 7 Panthers during the retreat from Falaise in August 1944. 4 had been knocked out by enemy fire or aircraft attack. 3 were abandoned with mechanical failures, primarily final drive problems, that crews could not repair in field conditions. The mechanical losses approached combat losses in proportion. American intelligence analysts reviewing the data recognized the strategic implications. German tank production had prioritized quantity over quality, accepting mechanical unreliability to achieve higher production numbers. The decision made superficial sense. More tanks meant more units could be equipped, more fronts could be covered. But the operational reality was that many of those tanks spent more time in maintenance than in combat. The actual combat power generated per tank produced was lower than it should have been, because reliability problems kept vehicles out of action. The French evaluation report from 1947 provided the most comprehensive post-war assessment. The French had operated Panthers under ideal conditions: peacetime use with adequate maintenance time, access to spare parts from captured German stocks, experienced German mechanics available to provide expertise, no combat stress accelerating wear. Even under these favorable circumstances, the Panthers proved unsustainable. The report documented that final drives averaged 150 kilometers between failures. Engine life was approximately 1,000 kilometers, requiring frequent overhauls. The transmission required constant attention to prevent failures. Track and suspension components wore rapidly. The French concluded that the Panther was in no way a strategic tank. The Germans had attempted to economize engine life by loading tanks onto railcars, even for very short distances of 25 kilometers. This approach might preserve mechanical components temporarily, but it demonstrated that the vehicle lacked the operational mobility required of combat tanks. The French phased out their Panthers by 1947, replacing them with American Shermans and French-designed AMX tanks. The decision reflected practical operational assessment overriding theoretical performance advantages. The Panther's superior firepower and armor protection could not compensate for its chronic mechanical unreliability. The Aberdeen evaluation program concluded officially in September 1945, though analysis of captured German documentation continued for months afterward. Captain Harrington prepared a final summary report that synthesized all findings from testing, intelligence analysis, and comparative studies. The report's conclusions were stark. The Panther represented a case study in compromised engineering. The original design had incorporated sound principles, sloped armor for better ballistic protection, a powerful, accurate gun, sophisticated suspension. But production pressures and material shortages had forced design compromises that fatally weakened the vehicle's reliability. The final drive represented the most serious compromise. The decision to use double spur gears instead of planetary gears saved months in production timing and simplified manufacturing, but it created a component that was fundamentally inadequate for the application. The gears were overstressed from the beginning, operating beyond their fatigue strength under combat loads. Material deficiencies compounded the design weakness, producing gears that failed predictably after minimal use. The problem was never adequately resolved during the war. German engineers attempted incremental improvements, modifications to bearing lubrication in September 1944, strengthened housing, mounting in, late production vehicles, better quality control in gear heat treatment, but these changes addressed symptoms rather than fundamental design inadequacy. The only real solution would have been redesigning the final drive with planetary gears, requiring extensive retooling and production delays that Germany could not afford. The Wehrmacht adapted to the limitation rather than fixing it. Extensive logistics support, rapid final drive replacement procedures, careful crew training to minimize mechanical stress, conservation of vehicle mileage through rail transport. These adaptations allowed Panther units to maintain some operational capability, but at enormous cost in maintenance resources and tactical flexibility. American tank development had followed a different path. The Sherman's design emphasized reliability and maintainability over maximum specifications. The tank's armor was adequate rather than impressive. The gun was effective rather than superior. The mobility was good rather than exceptional. But the engineering was sound. Conservative stress margins, proven components, accessible maintenance. The Sherman worked consistently under sustained operational stress. This design philosophy persisted in American armor development after the war. The M26, Pershing, M46, M47, M48, M60, and eventually the M1 Abrams all reflected lessons learned from analyzing both American and German approaches. Advanced capabilities mattered, but not at the expense of operational reliability. Impressive specifications were worthless if the vehicle could not sustain combat operations over extended periods. The Panther's legacy in military engineering education was profound. Defense contractors and military engineers studied the vehicle as an example of development failures. The rush to production before adequate testing, the design compromises forced by manufacturing constraints, the inadequate resolution of known problems, the acceptance of mechanical unreliability in pursuit of impressive specifications. The case study taught fundamental lessons. Production pressure should not override engineering judgment on critical components. Design compromises that appear to save time initially often create long-term operational costs that exceed the short-term gains. Mechanical reliability is not a luxury feature, but a fundamental requirement for combat effectiveness. Impressive specifications mean nothing if the vehicle cannot achieve them consistently under operational conditions. Captain Harrington left Aberdeen Proving Ground in October 1945, returning to civilian life after 4 years of military service. He had overseen evaluation of dozens of captured German vehicles, providing American forces with critical intelligence about enemy equipment capabilities and limitations. The work had been technical and unglamorous, invisible to the public, but essential to understanding the mechanical reality behind propaganda claims. The Panther testing remained one of his most significant contributions. The systematic evaluation had revealed that the tank German propaganda portrayed as invincible was mechanically fragile. The analysis provided American tank crews with exploitable intelligence. Panthers could be beaten not just through superior tactics or numbers, but by forcing engagement conditions that stressed their weak final drives until mechanical failure removed them from combat. Sergeant Michael Torres, the transmission specialist who had conducted comparative analysis of Allied and German final drives, also returned to civilian life. He resumed his career in truck manufacturing, bringing military experience to commercial vehicle design. The lessons from Panther analysis influenced his work. Reliability mattered more than peak performance. Conservative design margins prevented premature failures. Accessible maintenance reduced life cycle costs. Torres occasionally lectured at engineering schools about military vehicle evaluation. He used the Panther final drive as a teaching example. The photographs of broken gears illustrated fundamental principles of fatigue, failure, and design adequacy. The comparison with Sherman planetary gears demonstrated how proper engineering prevented problems rather than accommodating them. The Panther itself disappeared from military service within a few years after the war. France phased out its captured vehicles by 1947. Bulgaria and Romania, which received Panthers from Soviet stocks, operated them only until the early 1950s, before replacing them with Soviet designs. The mechanical problems made sustained operation impossible without German-level maintenance infrastructure. A few Panthers survived in museums and private collections. The vehicle at Aberdeen eventually moved to Fort Knox, then to Fort Benning when the armour school relocated. Museum visitors could examine the tank that German propaganda had portrayed as invincible, but they could not see the broken gears inside the final drives, could not understand the mechanical reality that systematic testing had revealed. The impressive exterior concealed fundamental engineering compromises that doomed the vehicle to operational unreliability. The final irony was complete. The Panther had been designed to achieve tank superiority over Soviet 34s and Allied Shermans. On paper, in specifications and theoretical capabilities, it succeeded. The gun was more powerful, the armour was thicker, the optical sights were better. But in actual sustained combat operations, the mechanical unreliability cancelled the performance advantages. American crews in Shermans with inferior guns and thinner armour defeated Panther units, not through superior equipment, but through superior operational sustainability. The Sherman kept running, the Panther kept braking. Over weeks of continuous operations, the advantage shifted decisively to the reliable vehicle rather than the theoretically superior one. The Aberdeen evaluation had documented this reality with scientific precision. Captured Panthers tested under controlled conditions failed mechanically, within distances that would be considered catastrophic for American tanks. The final drives broke predictably after 150 kilometers on average. Some lasted slightly longer, others failed sooner. But none achieved the reliability required for sustained combat operations. The engineering analysis revealed why. Double spur gears overstressed by 50%, material deficiencies from alloy shortages, design compromises forced by production pressure, inadequate resolution of known problems. The combination created systematic mechanical weakness that no amount of crew training or maintenance expertise could overcome. German engineers understood these problems. Internal Wehrmacht reports acknowledged the final drive weakness explicitly. But the production system could not implement fundamental fixes during wartime. The Panther continued rolling off assembly lines with final drives that would fail after minimal use, because stopping production to redesign components was politically and militarily unacceptable. The cost was measured in abandoned tanks across European battlefields, Panthers sitting intact beside roads, immobilized by broken final drives their crews could not repair. Tactical limitations, as commanders planned operations around mechanical constraints rather than tactical opportunities. Psychological burden on crews who knew their vehicles might break down at critical moments. Vast maintenance infrastructure required to keep unreliable vehicles marginally operational. American tankers who examined disabled Panthers after battles often found them mechanically failed rather than combat damaged. The distinctive pattern of an intact hull with no penetrations, tracks undamaged, but final drive housing open where German mechanics had attempted field repairs before abandoning the effort. The Panther had defeated itself through mechanical failure without requiring enemy action. The story of the Panther's final drive became a definitive example of the difference between engineering specifications and operational reality. The tank looked formidable in technical documents. Propaganda films showed it crushing opposition. Intelligence reports suggested American crews should fear it. But systematic evaluation revealed the mechanical truth. The impressive specifications concealed fundamental weaknesses that made sustained combat operations impossible. Captain Harrington's work at Aberdeen had stripped away propaganda and revealed engineering reality. The methodical testing, careful documentation, systematic analysis provided American forces with knowledge that transformed the intimidating Panther into an understood mechanical system with exploitable weaknesses. The final drives would fail after approximately 150 kilometers. This was not speculation or propaganda. This was verified. Data from testing multiple vehicles from multiple sources. The knowledge saved American lives. Crews facing Panthers in combat understood that the imposing opponent had mechanical feet of clay. Force engagement conditions requiring sustained maneuvering. Extend operations over multiple days. The Panthers would disable themselves at rates that German logistics could not sustain. The mechanical unreliability was as effective as armor penetration in removing Panthers from combat. The profound lesson transcended the specific vehicle. Military equipment design required balancing multiple competing priorities. Performance, reliability, manufacturability, maintainability, cost. The Germans had prioritized impressive specifications and rapid production, accepting mechanical unreliability as an unavoidable consequence. The Americans had prioritized operational sustainability, accepting adequate rather than maximum specifications to ensure vehicles functioned consistently under combat stress. The American approach proved superior not because Sherman tanks were better than Panthers in head-to-head comparison, but because Sherman tanks were still fighting after Panthers had broken down. Reliability was not a secondary consideration. It was fundamental to combat effectiveness. A marginally capable vehicle that worked consistently generated more actual combat power than a theoretically superior vehicle that constantly failed mechanically. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.